We will now look at how to compute the derivative of an exponential function. Recall that an exponential function is a function of the form f of x equals f naught times a to the x, where f naught is f of 0 and it has a constant relative change for delta x equals 1. That is, as x increases by 1, f of x gets a times bigger. Now, we want to compute the derivative of f of x. That is, we want to compute the derivative of f naught times a to the x. Since f naught is a constant, we can factor it out of the derivative to have f naught times the derivative of a to the x. What we still need to figure out is how to compute the derivative of a to the x. To compute the derivative of a to the x, let's start out with an example. Let's try a equals 2. So we're looking at the function f of x equals 2 to the x. Recall that we already computed f prime of 1 to be 1.38629 in a previous video. To understand f prime of x in general, let's look at a table where we keep track of many values of x and f prime of x. Starting with, when x is 1, f prime of x is 1.38629. What about when x equals 0? What is the derivative f prime at 0? To find this, let's compute it the same way we computed f prime of 1, which was by our definition of the derivative, f prime of x equals the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Applying this to our example, f of x equals 2 to the x, we find approximations for f prime of 0 by computing f of 0 plus delta x minus f of 0 all over delta x. And then to get the exact value of f prime of 0, we need to take the limit as delta x goes to 0. As we did in finding f prime of 1, let's keep track of our approximations of f prime of 0 along with our value of delta x. In our calculations for all values of delta x, we can see that f of 0 plus delta x is 2 to the 0 plus delta x, or 2 to the delta x, and f of 0 is 2 to the 0, which is 1. So in calculating our approximations for f prime of 0, we need to compute 2 to the delta x minus 1 all over delta x. Let's start with delta x equals 1. Here we have 2 to the 1 minus 1 over 1, which is simply 1. So our first approximation for f prime of 0 is 1. Now let's take delta x to be 0.1. Here we compute 2 to the 0.1 minus 1, all divided by 0.1, to be 0.71773. So our new approximation for f prime of 0 is 0.71773. Carrying on, we take delta x to be 0.01. Here we need to compute 2 to the 0.01 minus 1 all over 0.01, which comes to 0.69556. So our next best approximation for f prime of 0 is 0.69556. Carrying on, we take delta x to be 0.001. Here we compute 2 to the 0.001 minus 1 all over 0.001 to be 0.69339. So our approximation for f prime of 0 is 0.69339. Notice as we take delta x to be smaller and smaller, our approximations vary less and less. Now let's look at delta x equals 0.0001. Here we compute 2 to the 0.0001 minus 1 all over 0.0001, which comes to 0.69317. So our next approximation agrees to the first 3 decimal places, which is 0.69317. Moving delta x even closer to 0, we look at delta x equals 0.000001. Here when we compute 2 to the delta x minus 1 all over delta x, we get 0.69315, which is extremely close to our last approximation. Doing one more, let's take delta x to be 0.00000001. Here we compute 2 to the delta x minus 1 over delta x to be 0.69315, which is the exact same as our last approximation. So we can be confident that as delta x gets even smaller than that, our approximation of f prime of 0 will not change by much. So we can conclude that f prime of 1 is roughly 0.69315. Let's bring this back to our previous table. We just found that when x equals 0, f prime of x equals 0.69315. To get a better understanding of f prime of x, though, we need to have more data points. So let's now compute f prime of 2 in the same manner that we computed f prime of 0 and f prime of 1. Now we will use the definition of the derivative in our example f of x equals 2 to the x to approximate f prime of 2 using f of 2 plus delta x minus f of 2 all over delta x, and then taking the limit as delta x goes to 0. Again, it'll be useful to keep track of our approximations of f prime of 2 along with delta x using a table. And also, it will be useful to use that f of 2 is 2 to the 2, which is 4, and f of 2 plus delta x is 2 to the 2 plus delta x in all of our calculations. Let's start off again with delta x equals 1. Our first approximation of f prime of 2 is 2 to the 2 plus 1 minus 4 over 1, which is 4. So we will add this to our table. Next, we take delta x to be 0.1 and compute our approximation to be 2 to the 2 plus 0.1 minus 4 all over 0.1, which comes to 2.87094. So our next approximation for f prime of 2 is 2.87094. Now we take delta x to be 0.01 and calculate 2 to the 2 plus 0.01 minus 4 all over 0.01, which comes to 2.78222. As we add this to our table, again it's worth pointing out that as delta x gets smaller, our approximations get closer together. Carrying on to delta x equals 0.001, we calculate our approximation to be 2 to the 2 plus 0.001 minus 4 all over 0.001, which comes to 2.77355, which agrees with our last approximation in the first decimal place. Next, we compute our approximation of f prime of 2 using delta x equals 0.0001. Here we compute 2 to the 2 plus 0.0001 minus 4 over 0.0001 to be 2.77268, which agrees with our last approximation in the first two decimal places. Moving on to delta x equals 0.000001, we calculate 2 to the 2 plus delta x minus 4 over delta x to be 2.77259, which agrees with our last approximation in the first three decimal places. Moving delta x even closer to 0, we take delta x to be 0.00000001. Here we compute 2 to the 2 plus delta x minus 4 all over delta x to be 2.77259, which agrees completely with our last approximation. So again, we can be confident that as we take delta x to be even smaller, our approximation of f prime of 2 will not change by much. So our approximation of f prime of 2 is 2.77259. So when x equals 2, our approximation of f prime of x is 2.77259. If we were to carry this calculation on for x equals 3, we would find in similar fashion that f prime of 3 is roughly 5.54518. Before we move on to x equals 4, let's look for a pattern in our values of f prime of x. Notice that as x increases by 1, our function f prime of x doubles, starting at 0.69315 up to 1.38629. Doubling again, we get 2.77259, and doubling once more, we get 5.54518. So it should not be a surprise to us that when we compute x equals 4, the derivative f prime of 4 will be twice as big as 5.54518, which is 11.09035. So we have that f prime of x is a function which doubles each time we increase x by 1. But that means that f prime of x is an exponential function with base 2. In other words, f prime of x equals some constant k times 2 to the x. But what is k? Remember that k is our function evaluated at 0. In this case, our function is f prime of x. So k is f prime of 0, which is 0.69315. We might be curious where the number 0.69315 came from. It turns out that it is the natural log of 2. So we now know our derivative. F prime of x is the natural log of 2 times 2 to the x. In general, the derivative of a to the x is the natural log of a times a to the x. It is worth pointing out that if we use a equals e, we find that the derivative of e to the x is the natural log of e times e to the x. But the natural log of e is just 1, so the derivative of e to the x is e to the x, which is one reason why mathematicians like to use base e, because it makes our lives easier once we get to calculus.